couldn't quite finish this example, and so rather than rushing, I figure I'll just take an extra minute or two and do it right. So I'm trying to solve this integral. This is not holomorphic, so I can't use Cauchy's theorem, but it looks kind of like the Cauchy integral formulas, including the variation, except the problem is you can only have one bad point, and I have 0 and 1 inside my original green circle. So what I do is I'm just going to split it up. I'm going to do make a slice there between the 0 and 1, and a slice there, which these actually overlap, and they just cancel themselves out since they go in opposite directions. So what I can do is I can say, take this green chunk and the blue, green and blue makes red apparently, and then take this green chunk and the orange, and that makes purple, and I call that alpha and beta. There's only one bad point with an alpha, 1. There's only one bad point with an beta, 0. So what I can do is I can say, well, if I add these integrals together, that's the same as adding green and blue and orange and this left half of the green together, and I may as well just do the green and the blue together, and then the left half of the green and the orange together, called alpha and beta. And then I can just rewrite my denominators, or my numerators and denominators like this. On alpha, the only bad point is 1. So I'm going to leave the 1 in the denominator, and then what I have, let's just make this a little more readable. And then what I have is this thing here is holomorphic on alpha. On alpha, you don't go anywhere near the origin. So on alpha, this is holomorphic. Z minus 1 causes the entire integrand to be not holomorphic. So this is a classic Cauchy integral formula one. So I just do 2 pi I times, we normally say f of w, but I'm not going to write f of w. I'm going to write f of the bad point. The bad point here is 1. But f of 1 means I just plug in 1 into the numerator. F stands for the numerator when you're talking about the Cauchy integral formula. So actually, the way this is written is this is going to be written as 1 over 1 squared. That's the value of this integral, this alpha here, which is the blue and the right half of the green. And I can use similar reasoning over here, except I need to use Cauchy's variation, right? This is a z squared, a z minus 0 squared. So I need to use 2 pi I times the derivative times f prime of w, where w, the bad point here is 0. So I'll just erase that and plug it back in. Zero. And so the derivative, right, I can just compute this over here on the side maybe. 1 over z minus 1 prime is equal to negative 1 over z minus 1 squared. So what I get is 2 pi I times 1, so I'll leave that, plus 2 pi I times, well, I plug in 0 into negative 1 over 0 minus 1 squared. Oh, well, that's going to give me negative 1 equals 2 pi I minus 2 pi I equals 0. So in this case, the integral evaluates to 0, which is the answer that we would have gotten if we just said, oh, the circle contracts and we can use Cauchy's theorem. The problem is that's bad reasoning, because you can only use Cauchy's theorem if the integrand is holomorphic on the entire region. So that's a longer explanation than I would have liked for the second part, but that's what you got. So we're done. Thank you.